Good day, everyone. Happy Friday. I'm Jack Van Horn from the University of Virginia, and I am very proud to welcome you to this edition of our 2022-2023 Foundations of Biomedical Data Science Seminar Series. This lecture series is supported by UVA's Integrated Translational Health Institute of Virginia, the UVA Brain Institute, the College of Arts and Sciences, the School of Data Science, and through a grant from the National Institutes of General Medical Sciences. Since 2016, the Foundations of Biomedical Data Science Seminar Series has focused on the use of data science methodologies, artificial intelligence, deep learning, and statistical modeling as they pertain to different themes in the biomedical and health sciences. This year's theme is data science and the public health consequences of the COVID-19 pandemic, where each Friday we enjoy presentations from leading thinkers about the issues, the promise, the opportunities, and the hurdles associated with understanding the secondary health effects of COVID-19. These include delayed health checkups and treatments, mental health, drug abuse, increased obesity, and the long lingering health effects associated with the SARS-CoV-19 virus. Participants selected in our Biomedical Data Science Innovation Lab program will leverage these presentations as vital material for our culminating in-person grant project development workshop to be held at the Lodge at St. Edward's Park in Seattle, Washington in June of 2023. I am delighted to welcome our speaker today, Dr. Jason Hsu from the Department of Statistical Science at Duke University. Jason is an assistant professor in the Department of Statistical Science with a secondary appointment by courtesy in biostatistics and bioinformatics. Prior to joining the faculty at Duke, Jason worked at the University of California, Los Angeles with support from the NSF Mathematical Sciences and Postdoctoral Research Fellowship. He completed his PhD in statistics at the University of Washington in Seattle, where his work was funded by an NDSEG fellowship. And Dr. Hsu grew up in Tucson, where he received his BS in mathematics from the University of Arizona in 2012. In continuing with our 2023 Biomedical Data Science Seminar Series theme, today's lecture is entitled Likelihood-Based Methods for Fitting Stochastic Epidemic Models to Noisy Data. Due to noisy data, observational data, and nonlinear dynamics, even simple stochastic epidemic models such as the SIR model present significant challenges for inferences. As a result, likelihood-based inference is typically considered out of reach in the presence of missing data, and practitioners often resort to simulation methods or approximations that may bias conclusions and reduce interpretability. Motivated by a number of these challenges, Jason is going to share with us today how a data-augmented approach successfully learns interpretable epidemic parameters and scales to handle large realistic data settings efficiently. As always, we are streaming this lecture live and for recording via YouTube. If you are watching on YouTube, thank you for joining us. Also, our specially selected 2022-2023 Biomedical Data Science Innovation Lab participants and alumni are encouraged to submit any questions they have via the chat feature in their Zoom sessions. I will synthesize these questions and ask them on your behalf during the last 10 minutes or so of the lecture. And with that, welcome, Jason. We are so excited to hear from you.
Thank you so much, Jack, for the introduction, and thank you all for being here and for the invitation to speak in this great series. My talk, as you might be able to tell from the title, is going to be biased toward statistical inference. I'm a statistician, and some of the work is kind of technical in nature. It's methodological, but I'm really excited to talk about it with such a broad audience coming from all sorts of different backgrounds, which, as we've seen, is so important to address everything since this pandemic. A lot of these challenges kind of go back, of course, in a long mathematical tradition for modeling epidemics. A lot of this work has been around since before the pandemic, but also the sort of realizations we've encountered with the data that have come up and the sort of new ways we can study dynamics as a disease moves through a population has spurred a lot of new development for these methods alongside computational developments in the modern world. So without further ado, I'll go ahead and get started on my slides. I do want to say, again, I tried to make some of the technical stuff there for concreteness, but also I try to make it so that the overall theme will hopefully come through even without understanding all of the technical details. And I'm always happy to take questions, of course, for anything that's not clear. So, of course, this is kind of about epidemic models, and we know that this is related to the pandemic for this year's theme. But I just want to emphasize that in many disciplines, beyond just sort of the spread of disease, for instance, computer scientists might need to look at how ideas or information or memes spread across a network. And of course, economists might want to look at how behavior spreads among individuals in some kind of community. But in many of these disciplines, we want to understand the spread of something like disease-like. And in my own view on these models, because there's such a great literature from so many different disciplines, we think that at least some of the things we want our models to reflect is the mechanics of how this disease or contagion is spreading. I'm a statistician, so I'm biased toward wanting some kind of randomness. So I'm going to be talking about stochastic models where not everything is predetermined by the specifics of the rules you specify and the parameters, but there is some randomness in how the process evolves. And one thing that I'll mention in this talk is that we'd like to account for some structure and rates of contacts in the population. And that's something that's not always done in sort of many of these studies today, even though we know that these rates are going to have a big effect on how the disease spreads. And so why don't people account for all of these pretty simple things all the time? Well, basically doing sort of rigorous inference can be a challenging math problem, or even when the math is known, it can be a challenging computing problem. And this is true even in some of the simplest models that many of you have heard of. So what I'm talking about today is something called data augmentation, which is not a new idea. It's been around for a long time. And even in the 90s, people have studied some of these simple models under this perspective. But there are a lot of computational limitations to the general idea that we're hoping to revisit and revive. And in particular, our revisiting of this approach will hopefully be very complementary to the dominant ways that people look at stochastic models of disease, which relies on rather intensive simulation, as we'll see. So let's talk about these epidemic models. First, the compartmental models of infection, such as SIR, this is what Jack mentioned in my abstract. This is going to be the focus of the kinds of model we talk about today. And this goes back almost 100 years ago to the work of Sir Kermack and McKendrick, and it describes how a disease process moves between groups in a population where those individuals are grouped by disease status. So in the simplest case, you have susceptible people who are being infected by some population rate. Here it looks like beta times S times I. And then those people are going to, when they become infected, they move to the I compartment, which is the infectious individuals. And then those individuals will recover or be removed because of death or something like that from the population at some other rate, which looks like it's gamma times the infectious population. So in this very simple model, there's just two parameters, beta and gamma. And classically in their work, and they've also described general versions, even in that original paper, and there are many variations on such models. But these compartmental models, they were typically proposed and still mostly studied today under what we'll call a deterministic dynamical system. Okay, so when I say ODE, I mean that this set of equations, they're called ordinary differential equations, and that's how that describes the disease flow. But these equations just tell you basically curves that are preordained once you give me beta and gamma and the populations. So instead, what we want to talk about today is basically the analogous model, but it's going to be a stochastic or random version of those dynamics, okay? And so in this case, I'm basically going to replace that set of differential equations, without going into too much detail yet, by some random processes. In particular, this is going to be what's called a continuous time Markov chain. Now, in this model, when I have a realization of the curve like this, it's actually not smooth, which is what they would look like under that first model I showed you. Rather, the population can go, there can be little jumps depending on these random events that are occurring. And I would say that the parameters under this model can also be more interpretable, in addition to having randomness that helps us estimate the uncertainty in our parameters. So for instance, a lot of public health officials are very interested in estimating things like basic reproductive numbers. And oftentimes in words, such a quantity is defined as the average number of secondary infections caused by an infectious person. And so, that can be somewhat vague in a deterministic model. Even though there are equations to get at that, it doesn't always align with most layman's notion of the word average, right? Which is often a statistical average, like you take a lot of numbers and you average it. So in this case, if I have random variables, first of all, this quantity is directly related to the parameters, the interpretable parameters I want to estimate from the data. And furthermore, because it's a stochastic model, I really know what this notion of average means in an intuitive way. One other thing I want to mention is when we write down these models with equations such as this, it is assuming already under the hood that there's random mixing going on, which means that all the susceptibles and infectious people are bumping into each other uniformly and at a constant rate. So there's no structure in the population. Your behavior doesn't change depending on your disease status. And that might not be very desirable for studying outbreaks, especially things like COVID, when the behavioral contact patterns are changing very much throughout the pandemic with different policies and different behaviors. So this talk, we're not actually going to talk about COVID data per se. We're going to be motivated by a mobile health study that was collected by a colleague, Alison Aiello, in a study called X-Flu. And so in this study, there's a Bluetooth app that participants were given that actually pings when two participants are near enough and then stops pinging when they're far. And this is happening in real time. So over the course of the study, we can actually observe these contact networks between individuals. And as you see, just plotting some of the raw data at some of the weeks, we see that certainly it's not a complete network, which means not all edges are present. So of course, not everybody is bumping into everybody else at a constant rate. In fact, it's kind of sparse in terms of the density. And so we would like to, for instance, not only enable this rigorous statistical inference, but also make these models more realistic by incorporating such information. And so naturally, one might be interested in transmission in such a network, right? When we talk about this well-mixed setting where everyone's bumping into everyone, one way to kind of represent this in some mathematical object is, let's say we had a population of only 5 people. We're going to represent this by a complete graph, which means everybody has the potential to interact with everyone else. That's what the edges denote. But of course, if we observe network information or from, for instance, mobile data, we might know that person 1 was only in potential contact with person 2, 3, and 4. And so therefore the infection could only have spread that way if person 1 was infectious. Similarly, if you wanted to do contact tracing or something, and person 5 later got infected at this time, you might know that it could not have been one that was the source if you have this kind of data. And of course, there's a lot of recent growing interest in this setting. But even before getting to that setting, what I want to claim is when you want to do a lot of the traditional approaches that are kind of fully rigorous in statistical inference, even that simple model that I plotted on the first few slides is very difficult to fit exactly. Okay, and so I'm going to try to motivate why that is in a little more technical detail soon. But first, let's talk about what people do instead, because I know that there are a lot of papers out there in all sorts of disciplines that say we have this SIR model, this complicated model, and then we learn it from data. So when people say this, I'd say most of the time, especially if it's a model with a lot of bells and whistles, it's quite common that they're actually doing the inference or the simulation or the model fitting under some kind of approximation to the fully stochastic model anyway. Of course, you could have a deterministic model, but because those preordained curves will never match the data exactly, they will add some statistical noise distribution on top of that. So it's a mixture of something that's deterministic plus randomness that's not related to the process itself. And that might be a little bit subtle. There are also other stochastic process approximations. So there are other random processes, but you might need to simplify the dynamics. You might have it evolve discretely, stepwise through time instead of naturally in a continuous way. Or you might have an opposite thing where instead of keeping track of exact populations, you treat everything as a continuous number when you have a large population. These are called diffusion approximations. There's all sorts of approximations out there. So I think it's really important to know when you're doing inference under what model, because even though they're often called the same things like SIR or its variants, these little approximations can make big differences and bias your inference. Similarly, when you actually want to fit these stochastic models exactly, the models, the sort of predominant method for doing inference is often simulation-based. So there are things like sequential Monte Carlo, things called particle filtering, and they rely on simulating many realizations of the data from the model itself and seeing basically how well they match. And then the ones that match well, you upweight those parameters. This is a very cartoonish way to describe it, but the idea is that these methods are actually very flexible, very powerful, but they're pretty hard to implement, and they kind of can work on a case-by-case basis. When you have a data set where it just happens not to work well, it's something called either poor mixing. It can become degenerate and give you a solution that's just not interpretable at all. And finally, because they're so intensive, without really large-scale computational resources, it's hard to do this on large data sets. Okay. So what we'll focus on is instead a very classical thing in statistics where we make use of the likelihood directly to fit these models. And we want to take into account all these aspects of these models that I've just reviewed. Okay, so here's a little bit of technical detail, and I just want to illustrate the high-level point, but give some concreteness. So I've mentioned that in the stochastic case, we have these models being a class of continuous time Markov chains. And that means that The randomness comes from the fact that we have rates of things going on, in this case, infections and recoveries, or maybe more like contact rates. And then we wait a random variable amount of time until one of these events happens, and then the state jumps to a new process. And in a Markov process, that waiting time is something called exponential. And when we have such a nice distribution, this nice distribution has a lot of properties that makes things mathematically elegant. So the likelihood of the process, which describes how well a given set of parameters explain the data we observe, can be written down in a reasonably manageable form. Okay, it has this memorylessness property. So I'm not going to give a full overview of this, but for those of you who understand this, I hope this gives more concreteness. So this has such a nice form. If you were a statistics student, even in early years of your education, you would know that in classical approaches, if this quantity called the likelihood is telling me how well a given set of parameters theta supports my data, then to look for inferring the most likely parameters, it would make sense to try to maximize this quantity with respect to those parameters. So using some pretty simple calculus, I can maximize this and find things called the maximum likelihood estimators. Or if I want to take a Bayesian approach, which we'll focus on later, I can do something called specifying conjugate priors, which means updating my parameters given the data has a really nice form that's computationally one line for a computer. Okay, so we want to maximize this likelihood. And so far, the likelihood I wrote down for any continuous time Markov chain, which should include the processes I'll talk about, is actually really straightforward. What we need is we see that these quantities are functions of the total number of each type of event and the total time the process spends in each kind of state it has. So where is the difficulty arising? Why is this talk not over? Well, again, the challenge is that in real life, when we study epidemics and collect observational data from surveillance studies and things like that, we're almost never going to observe all of these quantities that inform these two terms that we need to compute these estimators. Just as an example, let's say we have incidence data, which is a focus of this talk. So every week, maybe this interval is describing 1 week, I've observed 4 new infections. Well, to compute those quantities, for instance, I'll need to know the infectious population. And if I don't know it, if I'm only getting data on new infections, it could have started with 2 infectious people and given the same number of recoveries, ended with 2 infectious people that week. Or it could have started with more infectious people, and if there was only 1 recovery throughout the week, I'd have 7 here. And not only do the different numbers of infectious populations account for the likelihood, but even if I change these times slightly for these 4 events, that will also change the likelihood. And so you could imagine if I can think about putting any number of possible events and computing all their probabilities and changing their time slightly, there's actually an infinite number of such step function looking objects, these continuous paths, that are consistent with my observed data, right? I can have infinitely many such shapes, not just these 2, that are consistent with the fact that there were 4 new infections. And so mathematically, this becomes a hard problem, as you might imagine. You have to integrate over all of that and account for their probabilities. So our goal is to develop a framework that can do so precisely. Okay, so we want to do inference based on that exact likelihood, even though we have that missing data. And we would also like to not only do this for SIR, but to expand it to relax some of the assumptions and make it more realistic for the kind of data we have today. Okay, so I know I spend a lot of time on the intro, but I really think that a lot of my goal in these kinds of talks is really to motivate the kinds of challenges that some people are either not even aware they're lurking when we fit these models, or for those of us who are in technical fields might be excited to make further contributions on in terms of the inference. So here we have a little bit of notation for sure, because the approach to deal with the missing data is something called data augmentation. So I want to describe it at a high level. I've already described that if I work with the data I observe, somehow there's an integral in the background. I need to somehow account for all the missing data. All those possible paths each have their own probabilities under that likelihood. And the likelihood, if I have the whole path, is the thing that I've shown you have a nice equation for. But the likelihood of my observed data somehow needs to average over all of those possible paths weighted by their possible probabilities. That can be a really hard problem. But if I don't know how to compute this red term, one thing we can do is, it's sort of technical, but statisticians have a well-used class of approaches called Markov chain Monte Carlo that makes use of a likelihood to draw samples from the posterior distribution and basically flipping this term around via Bayes' rule. Now, if I have access to this blue term, that's the part that I said even sort of young students in our department can do calculus and deal with, then we can maybe design a sampler that targets the distribution of both the unobserved states Z, as well as the parameters we care about. So theta denotes all the parameters, whether it's beta, the transmission rate, gamma, the recovery rate, additional things having to do with contacts, etc. And if I can draw latent variables to explore the possible values of Z and learn about their probabilities by targeting this Bayesian posterior distribution via something called MCMC, then now I can deal with the marginal distribution, or the distribution I cared about in the first place, which is what is the probability of those parameters given just the observed data. So this is something I don't have time to explain in one lecture, but this is well known, which is if you have this approach that somehow is generating samples of jointly your parameters you care about and the missing data, well, once you want to marginalize or get rid of the missing data and just look at the parameters given that posterior distribution, you're drawing them in pairs, theta 1, Z1, theta 2, Z2. You can just ignore the Z component. So think about putting them in a table and just covering your eye and looking at the thetas. That is now a valid draw from the posterior we care about, from the distribution, the probabilities of the parameters given our observed data. So now I'll describe one implementation of the strategy for that network case in a paper that's, again, with my collaborators, Alison Ayala, who is now at Columbia Biostat, and Alex Wolfowski, who is in my department, as well as a phenomenal graduate student who has since graduated, Fan. Okay, so this is going to be an instance of the strategy I've described. Now, the network process is actually going to be very simple. Like I said, we want to remove the assumption that this contact network between individuals, which of course will have more than 5, is not just a complete graph at all points. It's in fact something that depends on the observed links from our mobile health data. And so each time we'll observe some links which can be encoded in what's called an adjacency matrix, which means there's a 1 every time there's a link between person I and J. So I see a link between person 1 and 2, so there's a 1 here. There's also a link between person 1 and 3 and 1 and 4, but we don't see a link between person 1 and 5. Similarly, person 2 is only attached to person 1 at this time, so there's just the 1 in his row and zeros elsewhere. Now, this network is going to be changing over time, right? We're relaxing the assumption that it's complete and fixed. So this itself will also be some Markov process that's changing between zeros and ones in its entries. But what we'd like is that, well, these dynamics of how people interact will depend on the disease status, right? You might, if you're a 1, you're interacting with somebody, but now your friend is sick, maybe you're more likely to become a 0, which is to stop interacting with them, than if they were healthy. And similarly, if you're sick and you have a moral conscience, you might stop interacting with a higher rate than if you weren't sick. So let's define a similar process where if you are not linked, there's some rate of connecting called alpha, and the subscripts denote the disease statuses of these individuals that you'll start interacting. And similarly, there's some rate, for instance, in an exponential distribution with rate omega, you'll wait that long probabilistically before you break your link. We'll denote omega the link break rates. This will be superimposed on top of the same disease process that people have studied for a long time, but we see how it generalizes the network being complete. So whenever there is an edge with rate beta, which is that same beta transmission rate in the classical SIR model, you'll have I infecting J, right? Similarly, there's a competing rate, maybe gamma, like the waiting time is first, and then person I would recover before infecting person J. So now I is recovered and J remains susceptible. Maybe they'll have other neighbors that can infect them, or maybe they're safe. So we see, if you can imagine that if you had a complete network, then the total number of I's, infected people, that are in contact with J's, when all edges in the network are present, is actually S times I, if S is the total susceptible population and I is the total infectious population. And that's where the beta times S times I in the classical model comes from. But we're actually trying to replace that. So we see that at the individual level, you have infections, recoveries, and different kinds of link events on all potential edges in the network. So there's a lot of links, but they share these rates. Now, if we're assuming that we're just going to decrease the number of parameters by saying, well, the probability that 2 healthy people interact, whether they're already recovered or whether susceptible, doesn't really make a difference. So when we superimpose all of these things together at the population level, we have infection rates occurring at, this is sort of poor notation, but it's beta times SI of T. So SI of T is the number of SI edges, which in the complete graph is S of T times I of T. So this is slightly different from that. And this is changing all the time. recovery is occurring at a certain rate that's identical to the original process because individuals are independently recovering. That's not really dependent on their social network. And then, of course, there's all these link terms that we need to take a lot of bookkeeping on the number of different types of pairs. But overall, the dynamics are very tractable. It's still going to belong in this nice mathematical class of continuous time Markov chains. And if I wrote down the likelihood, even though there's tons of jargon in terms of the notation, you can trust that it's just as nice of a mathematical form that's manageable. Basically, there's these kinds of rates and there are these kinds of waiting times. And all of these things are computable. You can do the nice calculus here. It's the same simple form, but with more quantities and more notation. Okay. So just to validate the model, we ran simulation studies where, again, like you want to be able to recover the parameters under the model if that generated your data. So in these studies, we simulate data from our model, and we let the simulation go as we have more and more events. So we think that with more and more data, the more events we observe, the better our estimates should be. And so holding out the events and using our estimators, the sort of the forms we've derived, for each of these rates as the pandemic, simulated pandemic goes on, we do see that with more and more data, empirically, these estimates are becoming consistent. They're getting around the ground truth that we simulated them from, which is the black lines. And so this is just showing 4 repeats, but of course we did much more simulations in the tables in the paper, which you can check out if you're curious. Okay. So let's talk really briefly about the actual application to the XFLU data set, right? So we've validated the likelihood. We have a lot more simulation studies to look at things like frequentist properties. Are the confidence intervals correctly doing the nominal coverage? And that's all in the paper, and I'll give you references at the end. But let's now talk about how can we use this nice tractable likelihood in the more challenging setting I've been motivating this whole time, right? What I'm saying here is we still have the nice closed form solutions at the beginning of the talk. And if I simulate the epidemic, I can look at the event times and the dwell times, the things I need, but in more notation here, and I can estimate things correctly. So basically this checks that our formulas are correct. But again, I need to somehow apply this to the case where I have missing data, where I get to use this data-augmented strategy in accounting for the missing data by moving around latent variables for the unobserved quantities and proposing them efficiently to explore the space of unobserved quantities effectively. So in our problem setting, for instance, in the setting that this XFLU study motivates, you might have weekly health status reports. So of course, this is not monitored continuously in time. Every week we'll have sort of recovery reports from surveys on when these study participants feel better or when they're sick. And we do continuously observe the network, which is really nice, right? Because of those cell phones in the study, that part we don't have missing data on their link creations and deletions. But we do have this data split up by weeks. And so we know, for instance, in the Lth week, there are R sub L new recoveries, but we need to know the times of these events, just like that figure I showed you, or else we don't know the likelihoods, these nice blue quantities that we used for this simulation study. So now we need to do something augmented. We're not only estimating beta and gamma and omega and alphas, but we're also estimating all of these unknown times R, which is a much more high dimensional problem, right? You had a couple parameters in a nice model, and now you have a new variable for each person. Furthermore, the sort of structure of this latent space is quite constrained, right? It needs to obey the dynamics of the process, but it also needs to obey all the constraints from that observed network, right? You can't have somebody recover too soon if later their only link gets infected because that person needs some explainable infector. So you can imagine it's kind of the structure of this problem is rather tricky, but it's also a fascinating math problem. And so how does data-augmented MCMC look? There's really 2 steps in terms of describing the algorithm as a high level. So it looks easier than it is. The first is the data augmentation step. I mean, we have these observed data, but each one has a couple of missing variables, and we need to propose new configurations. You know, we don't know when the recovery times are. Let's propose different ones, move the potential times around, and based on the likelihoods, the probabilities of these configurations, learn things jointly with the data. So we need to be able to propose those recovery times and compute their probabilities under the current parameters as well as all the constraints by our data. Now, given the current setting of potential recovery times, and we can now update the parameters. And this kind of step is going to be nice. This is, again, the whole idea of having a nice model with a good, well-behaved likelihood function when all the data are observed, is because when I fix the potential configuration of the unobserved data in this completed setting, I can then do a nice parameter update. I can learn beta and gamma and everything else well. So we're going to alternate between proposing things that we don't have, like imputing the missing data in some sense, and then using all that information to have a nice mathematical object that we can use to learn the parameters. Okay? And so there's a lot of theory on why this is actually doing exact inference under the model. It's moving away from these biased approximations, which again are very effective, they're very useful. But you could imagine at the very least, if this becomes feasible, it actually serves for the first time as a baseline where you can use a faster, fancier method. But if you don't have guarantees on that method, you can compare how well it's doing in a setting with this method. And then if it's doing well, you can feel more confident in using it for settings where this might be difficult. Okay, so here's the high-level idea. Again, there's too much notation, but I hope I've explained the idea. And then the first step, like I said, is by far the harder step. You have to propose these things. I've alluded to the fact that they need to respect all the constraints from the network. And so I'm actually not going to go into this slide. What I want to do is just emphasize the result, which is this really was the work of that phenomenal graduate student. Fan was able to derive a step that not only moves around those unknown times in a way that's guaranteed to respect the data, because you could imagine, you can have a simple algorithm that says, oh, well, this person recovered too soon and there's a contradiction, so I now need to add some time to their recovery. When you have a clunky algorithm that just moves things around until all the constraints are satisfied, at the end of the day, the probability of all the things you chose to do in those steps with all these if statements can be a messy thing to work with. Instead, the step that we have for step one is going to respect all the constraints, but actually be what's called a conditional draw from its distribution. So what we mean is that the way that the algorithm proposes these missing values is exactly according to the probabilities they should be distributed under, so that we get to accept every proposal. We don't have to reject some because the probability was too low. So that's something, again, quite subtle, but if you work on Markov chain Monte Carlo, you'll immediately recognize sort of the advantages to having something that's what's called a Gibbs step, or a conditional draw from the probability distribution, given everything else. So I hope it won't get any more technical than that, but I hope the high-level idea makes sense for those of you who aren't technical. So what I mean, like I said, is once you have the proposed missing data, all of the updates for the parameters are really, really nice. So in this case, the formulas look kind of crazy, but this is one line in a computer in R. And when you have functions like this, sampling from a known distribution, like a gamma function, it's super easy, super fast. And so we're very happy with these kinds of estimates every time we have a sampler. And so the sampler alternates like this and tends to perform quite well. So I don't want to talk too much about the real data, because what I really want to focus on in this talk is just giving an overview of the methodology. But we should at least convince you that this was able to work well on the motivating example. So in this case, we have a study on college campus of flu-like transmissions. And it's quite complicated because we have about 600 students over 10 weeks. There's a little break in the middle. We have tons of network events observed, and we definitely observe low network density in the raw data, which motivates the fact that we need to relax this well-mixed assumption in these models. Now, just going on to the analysis, we were able to run that data-augmented MCMC. And so for the first time on this data set, we were able to do rigorous statistical inference on jointly estimating all the parameters, right? So we have the likelihood of this exact model, and then we're able to do not only estimation, so here we're reporting the posterior means of all the parameters, but we also have, the corresponding uncertainty quantification. So right now I happen to be reporting the 2.5 to 97.5% quantiles. So in this case, 95% posterior credible intervals. And again, the numbers might not mean too much for you. This is some study of dynamics of an outbreak on a college campus, but it's really for the first time the methodology is saying that here's estimates jointly, and in a fully stochastic model that incorporates the dynamics of the network. And not only that, but if you believe that this is your model, right, which is a big if, this is something that's really important. If you believe that this is your model, then the uncertainty estimation coming out of it is exact, right? So this is exactly the way to quantify how much faith you should have in your parameter estimates if you believe in the model. And there's a whole other can of worms there, which the likelihood actually really helps with. So if you don't know whether this is the model, because there's overall likelihood scores of these best estimates of the parameters, you can do all sorts of things that are rigorous, that are steeped in information theoretic criteria to do model selection, to ask yourself, is this model sufficient to explain the data? Or for instance, on the other hand, is it too rich? Did I put in too much stuff in the model and I'm at risk of overfitting so that my predictions are unstable? So all of these things statisticians are very aware of, that we really like to make predictions, to make inferences, and to draw conclusions from the data in a principled manner. A lot of these things revolve around this likelihood function. So the purpose of this is to really motivate that we can do likelihood-based inference for these models, even though a lot of people have sort of written that approach off as intractable. And just to actually talk about the estimates a little bit, we do have sort of sensical estimates based on the pilot studies that didn't have statistics for all of these parameters. They're not super easy to interpret. They're interpretable, but it's not easy to look at the table because of scaling. For instance, this rate looks so high, but it's because there are much more links between healthy people than others. Most of the people are linked but healthy. But it does, just to sort of interpret some of these things, there's a strong internal force of infection because we do have an external infection rate, which details are in the paper. And there's slow transmission across the campus with quick recovery. And in general, the contacts were very short. And the contacts being short could have been estimated independently, of course, from the data. But now we're having the dynamics of that affect our estimates of the parameters. Again, if we did not account for that, these parameter estimates could be very biased, which we've seen in the paper as well, and not included in these slides. Great. So in this first paper, the one I've been focusing on for the core of this talk, we've already seen that we can design these generative models in the tradition of these compartmental models, but also relax some of these maybe stringent assumptions, such as well mixing. And in this case, it describes the interplay between the disease process and the contact process, right? Not only are we seeing how the disease progresses conditional on a network, but also how does the network's rates change conditional on the current disease status of those people. So it's really interweaving. And of course, statistically, the whole idea is to enable exact inference so that if you believe in a certain model, you can know that your estimates are correct and the uncertainty, more importantly, is correct. But furthermore, if you don't know which model to choose, you can have this criteria to select models within a class. Now, I would say there's still a lot of limitations. So this is one thing I want to talk about for the remainder of this talk. Of course, we have certain mathematical assumptions. Right now, we were talking about Markov models, where there's an exponential recovery time and an exponential time for infectiousness. And many people have observed that this is not true for many diseases. It's not a good fit, right? So right now, we're trying to see, well, given that we've revisited this augmented approach for posterior inference, for Bayesian inference, how can we build upon this foundation to expand the class of model complexity, model realism, so that not only is the inference correct under the model, but we can do this for more and more models that people want to investigate. So just a couple previews here. We have some new work that not only is going to deal with the stuff in missing recovery times, but also looks at when you don't even have any information on the infection times of individuals. And that actually makes the problem much harder because these things are not only very high dimensional, but quite correlated with one another. In this same line of work, we're going to be able to accommodate the semi-Markov case where these times are not necessarily exponentially distributed. So for those of us who do mathematics, you might be aware that this is a big leap forward because it really changes the whole structure of these likelihoods and everything else. And again, this stuff has been investigated in the past, but has really been limited to small outbreaks and requires a lot of compute time, whereas our current directions using this data-augmented approach and these really nice proposal densities that we've engineered is able to do this inference on a single laptop, like a regular MacBook, for really large outbreaks in just minutes. Right? So this is a huge leap compared to a lot of the existing methodologies in terms of computational time. And of course, some of the existing methodologies, the dominant approaches for stochastic models are much more flexible than what we have for now. But like I said, we're building upon this foundation, very excited for these future directions. I'll probably skip this slide, but it's trying to tell you that to design these nice effective proposals, we really need to just come up with similar stochastic processes with slightly simpler dynamics that are more mathematically tractable. And unlike these other approximation approaches, which then does inference under that simpler process, we can use these processes to explore the latent variables, doing step one in the data-augmented approach, but then correct their likelihoods so that at the end of the day, we're actually doing inference under the exact process, the original one that we posited. When we have such proposals, the step one, the kind of latent variable update, can be really, really nice. You can look at that pseudocode here. You can generate the entire epidemic in terms of the infection times and removal times in basically 2 joint lines of code. So you don't need to do things sequentially. For those of you who simulate epidemics and know how intensive that can be, you can really place them down because of the sort of decoupled dynamics of these similar processes. So again, this is just a preview. I don't expect to cover 2 things in technical detail in one talk, but is the directions we're building upon from that. These approximations, even when you only have, let me see on the caption, you only have 5 observation times throughout a whole epidemic that dies out. And we see that the approximations are quite far from the original process in gray. But as you increase the number of observations to even just 10, you see that it's much more faithful. It's almost looking like the exact original process. And when you have more and more observations, which of course is more and more possible these days in the data we collect, it's basically identical dynamics as the target process. So it's really, really promising. And I'm really excited to share that work soon as it keeps coming out. We've also applied that kind of work to real data. And so many of you who study disease are familiar with this Ebola pandemic in Western Africa some years ago. And many of the studies, for instance, the World Health Organization, based a lot of their estimates on these deterministic models. And even there, they had to do a couple rather heuristic parameterizations of the transmission rates and things like that. Whereas we can finally apply this completely stochastic approach to analyze data of this scale in just a couple of minutes on one laptop again. So this is a big breakthrough in terms of computation. And of course, we really are just reviving classical ideas that do exact inference that have been around for a while, but with a new modern lens for the kind of data and computing resources we have today, and the sort of new advances in Bayesian statistical methodology. So sort of a lot of exciting things in analyzing all sorts of partially observed epidemic data. Okay, so I'll wrap up pretty soon here. I just want to close by saying that fully stochastic modeling has a lot of advantages, right? I kind of delved right into this, but why do we care about the stochastic model approach? I would say that they're a little more interpretable than these deterministic models, right? When you have things like the probability of an outbreak, that has meaning under the parameters in a stochastic model, where in a deterministic model, you just have curves dictating its size, but it's already going to have an outbreak, which is a strange thing to have when you're doing inference and predictions. The uncertainty quantification is more interpretable and also, coincides with the estimation when we have a likelihood-based inference. And eventually, when we build out this framework to have richer models that are more realistic to describe all the data we have, this will lead to very reliable forecasting and decision-making, right? We can quantify whether we're overfitting, we can quantify how well we're capturing the data, and the uncertainty quantification, the confidence or credible intervals coming out of the inference are trustworthy. Again, the continuous time Markov chain framework we focused on here is very classical for mathematicians and the long line of modeling alongside epidemiologists, but it's extensible in many open directions. We've already been relaxing some of these distributional assumptions to make this super flexible. And in one example here, we've relaxed the well-mixing assumption to incorporate networks, but we're also working to incorporate spatial data, all sorts of different sources from phylogenetic information. And again, like from a likelihood-based approach, there are ways to integrate these things naturally. There's still a lot of open directions and things we're working toward, as well as things that we'd like other people to work toward. So right now, we haven't really dealt with the case, which is very natural from a data perspective, to have multiple strains, multiple compartments, like not just in terms of disease status, but in strata of the population. We have been working already on different individual level covariates to add more heterogeneity to the dynamics and things like missing data under unreliable reporting rates. My colleague, Alexander Wolfowski, is already working on the network missingness problem, and I've been thinking a lot on more realistic random graph models for these network dynamics. We've been working on some things for change point detection when the force of infection beta is also changing through time. Again, you don't want it to be too flexible or else your model can fit anything, but so you want it to be flexible enough, but also parsimonious enough so that you don't have volatile predictions. And all sorts of things in particular, we'd want to really have hybrids, right? I've overviewed all this kind of work that I said this is complementary to, and I don't take issue with that kind of work. I just think that this line of work was somewhat abandoned because it was a hard math problem and it was computationally intractable. And I'm saying that it's not necessarily intractable if we're willing to think hard about this, but we can probably take it even further by looking for these connections explicitly with the other things that people are doing in this field, many of which is also very exciting methodology. So with that, I'll wrap up. I wanted to thank especially the student collaborators here. I've mentioned Fan Bu, who was the lead author on this network paper, and she's going to start a faculty position at Michigan's Biostats department. We're very proud of her. Raphael is currently a PhD student advised by me at Duke and is doing a lot of the really exciting stuff on computation for these fully missing data settings and the semi-Markovian settings. And Jenny Huang is an outstanding undergraduate, actually, who is unfortunately already committed to a PhD program for those of you who might be in the market to recruit talent. She's joining MIT's EECS program, and she's been working on a lot of the dynamic change point detection stuff for time varying transmission rates under these models. So I'll just leave you with this slide on some of the references, a partial list of references. These papers are under various preprint statuses, submission statuses, and publication statuses, and include my other collaborators who are really wonderful to work with throughout this whole process. So with that, thank you very much for your time and for listening.
Jason, thank you so much. Wow, what an interesting line of kind of attack on this interesting, challenging problem. And I'm sure lots of people have questions for you, and I hope they can ask them in the chat or maybe reach out to you directly via email. You mentioned exploring other multi-compartmental kind of approaches. Can you describe a few of what those might be? And also, what does that do to some of the computation, some of the math and computation times that might be involved?
Yeah, that's a great question. So there's a couple different directions, and I'm going to mention two of them. So we talked about sort of, I guess it's on this last slide, for things like multiple strains and compartments. So one very natural thing, I focused on SIR here, but there's of course ones with more stages. There's SEIR, where the latent stage is even harder to observe. So for these kinds of models where there are more sequential stages, it's basically the challenge is to design these proposals in a way that is still identifiable. So you can actually explore the latent compartments in a way that you can learn from the data, because you can't observe, there's more that you can't observe. And so the mathematics needs to change. On the other hand, when it's simply sort of more levels, like maybe I have the identical model, but I have adults and children, right? And this is a big thing, right? Epidemiologists care about how the dynamics with young people might be different from different strata, what I would call strata in the age structure, other structure in the population. And so in those cases, I would say a lot of the mathematics goes through, but then the computation is what's increasing in complexity, right? You could imagine it's not necessarily just double the computation when you have double the strata, but because of the connections between things and how you posit the relationships, it can grow even faster than that in complexity. So there's all sorts of these sort of trade-offs to balance, but I think it's absolutely something that's worth investigating, right? So this kind of heterogeneity, you can have, for instance, household structure as well, right? You would have two levels in a hierarchy where you have this kind of network thing between people, then you also have household units and their dynamics. So there's kind of going this way and going this way in terms of expanding the compartments, and there's different challenges that arise. Yeah.
One of the characteristics of exponential distributions and sort of embedded in Markov chain modeling is the notion of memorylessness. And some people may not be familiar with that, what that concept may mean mathematically and what it means in the context of these models. Would you mind doing us a solid and explaining what that means?
Absolutely. I barely mentioned that at all. And I think, I'm trying to tiptoe between too much technical difficulty, but like also this is actually a really important point, right? So like I said, these random models, they're processes. So the time between events has to follow some random variable. And the reason that people like to choose exponentials is because they're really mathematically convenient. They have this memorylessness, which is to say that, let's say, person one is sick in week one, week two, they're still sick, right? The memorylessness is saying that, well, when I look at the mathematical properties, like the probability they recover in a certain time, I actually don't even need to think about the fact that they were already sick for a whole week. Okay. And that of course makes the math easier, because otherwise I incur this mathematical debt of having to remember exactly when everybody got sick and changing the probabilities based on how long they've already been sick. Now, on the other hand, now that I've revealed that, you could absolutely imagine why an epidemiologist would say, hey, that's not a really realistic assumption, because the exponential distribution mathematically also has what's called fat tails, which means that there's a lot of probability for the extreme events as well. So you could imagine, well, if every time I'm like giving a fresh new coin flip on whether this person is going to recover, if a particular person happens to have, survived for 3 weeks in a row and the recovery period tends to be much shorter than that, this is a really unlikely event. So the model is kind of giving probability mass to something that's unrealistic biologically. So many people want to have distributions that are more realistic, that have a memory property that says, well, this person hasn't recovered yet, but already been sick for 2 weeks. So the probability they recover is very high. The exponential one, that probability doesn't change over time, which helps us mathematically, but is not that realistic. Like I said, we have new work that actually addresses this very flexibly, but is not focused on here today. That's a great question. Thank you.
You mentioned also that some of the assumption about that exponentiality may not be always true. Are there any other shapes of distributions? Shape, I guess, kind of morphometry of other distributions, which might be suitable for the modeling, may have memoryless processes, or maybe just, also convenience for a variety of reasons?
Yeah, no, that's also a great question. So, I mean, in particular, like I said, we've been developing methods for all sorts of general processes with different what's called renewal distributions. Mm-hmm. But just two that I'll mention, something that people have looked at in the past is gamma distributions. And the reason is because statistically, some gammas have multiple parameters, but some members of that family of distribution are actually the sum of exponentials. So it's kind of a very natural extension. Well, you could imagine that this is a larger class. And another thing that we've been working with is the class of Weibull distributions, and that has some nice ramifications from extreme value theory, which makes things more robust. So there's all sorts of different choices here, and we've only investigated a couple so far, but the methodology is general. And I think there's a lot of there's a lot of nice. Again, it's an interesting balancing act between finding things that are nice enough mathematically, but also rich enough to describe what's going on in a way that's satisfying to people who actually deal with the data. Right. So mathematically, exponentials are on one end of that spectrum. They're the nicest one, but they're just simply not appropriate for many, for instance, infectiousness distributions. So I would say a good starting point and something that's been looked at in the literature in different contexts are both the gamma family and the Weibull family.
Have you ever put any of these simulations like in motion to try to, in silico, create a little community that have a monkey with the assumptions of mixing rates and that sort of thing, and then kind of watch these probabilities play out sort of, again, in a little in silico petri dish? Does that make sense?
Absolutely, it makes sense. And this is something that we absolutely have done. I didn't really go into it in this talk. It's in the paper. I did mention, though, that there was a simulation study where we validate the equations. But basically, the way that works is that we specify the dynamics, the probability laws of the model, and we do simulate a little outbreak according to those rules. And then let's say we would pretend that we didn't simulate it and know everything. So we would now say, oh, I'm gonna throw away all the data that I get to see, except for the same sort of quantities I would see in an observational study. And that's super important to, then employ the methodology we developed on that setting where we're artificially only giving ourselves access to some data, but we're seeing how well we can learn the rest, right? So we've done all sorts of studies like that in the paper. To another part of the question, the interesting thing is, like I said, you can validate whether the inference is correct under the model you specify, but a sort of related challenge is, well, how can you simulate things well for unobserved quantities? So I guess what I'm thinking of is, in our case, we fully observe the mobile contact network. And so we can learn the rates and look at how that affects the transmissions. But now let's say, this is something I, again, didn't go into, but at the end I said, what if we could look at more realistic random graph models? And what I mean by that is, if you now have a setting where you want some network to describe behavior, but you're in a setting where you don't have, for instance, a cell phone study. So you don't observe the network, and now you want to simulate that network like you're suggesting, in a way that's plausible, that might explain the way people are moving, even though you don't observe it, right? So, right, in our methodology, I've motivated how we don't observe the recovery times, but we're able to infer them. This is sort of an even harder problem where you don't observe the networks, but you'd like to posit a model that you can simulate potential networks. And so that can be hard because a lot of times the nice mathematical models, many of them might not reflect some things you tend to observe in real life. So you might have a certain class of models you observe and find there's like edges that are added and removed, but then many of the observed networks don't have as many triangles as you would see, because in real life, my friend of a friend is more likely to be a friend here. And then if you tweak it by adding, closing triangles when you have two friends, but then their friends of friends aren't friends yet, that could introduce new triangles. So there's all sorts of things that have been, persistent problems in the literature that are interesting facets to think about when you do simulation. Yeah.
So some of your equations have probably struck fear into the heart of several of the biologists who are watching today. What sort of comment would you have for them about wanting to participate in activities that are like this, right? What would they get out of doing something like this as somebody who is a, card-carrying biologist, for example?
Yeah, that's a great question too. I think it's part of it, the difference in things like interpretability and what I keep saying, the uncertainty quantification. I think that difference is a little bit subtle, but it's something that I think biologists would absolutely care about, which is, for instance, if I have a deterministic model where the curve is governed by the parameters, like I said, when you observe counts, it's never going to pass perfectly through that deterministic curve. So what a lot of approaches do that fit the model to data is they have that curve plus just some probability distribution. Like I have that mean, that curve describes the mean number of infections, but then I have either Gaussian or binomial measurements from that curve. And that amount of noise from those distributions allows me to have at least a likelihood of my data that's not zero, right? It can be explained. It's like, oh, it didn't match this curve, but because I've only observed a noisy version. So now if I'm a biologist and I'm plugging this into maybe statistical software where I don't have to look at these scary equations and I get confidence intervals out of it, well, what does the confidence interval mean? The only probability in that model I just described is coming from the measurement error, because I had a completely deterministic process for the disease, and then the probabilities are on the measurements of how I observe that fixed curve. So you have to kind of think it's a little bit subtle, but it's like all the uncertainty can be interpreted as my measurement uncertainty of a process that's fixed, okay? So then when you estimate beta, and then you have a confidence interval, it's just measurement error on beta that's, it's not saying that if I have a quantity, like I said, in these models, if R naught is beta over gamma, basically normalized by the population, I can't think of this as a statistical average if beta and gamma are things corresponding to a fixed curve. And I have to think about it as some other thing that now has uncertainty around how it was measured. Whereas in these stochastic models, which you do run into these equations, this is a much more natural quantity because it's describing the uncertainty in the random process, right? Because I'm now envisioning the disease spread itself as a random process. I think that's extremely important. And I don't think that it's always a bad idea to use deterministic models, but I do think it's important to know how to interpret the uncertainty coming out of your inference. And so the only way to tell people to please look at these equations is to say, well, look how important it is in sort of the repercussions of knowing what model you're working with, right? And then if I had to just ease the notation, ease the equations themselves, I would just say that you got to trust that even though there's a lot of notation, these things are nice. Like if I give notation condensed things, these equations can be derived pen and paper in a couple minutes. And furthermore, the whole idea is that there's a lot of bookkeeping when I write that exact same equation in a specific instance, for instance, in our model. But even though these equations do look daunting, like they really are things where if I have the bookkeeping to like look at these quantities from the data, I could write down these commands in R in a couple of minutes, right? I could just put them in, and we did the math so that you can put in the equations. And furthermore, we'd hope to make this even more general, where we have user-friendly software, as long as it's the high-level idea is clear, which is that there's a stochastic process model, and the inference for the probabilistic quantification corresponds to the uncertainty in the process itself. I hope that's a little bit long-winded, but I hope it makes sense.
It does. Thank you, Jason. Jason, this was really wonderful. Thank you for sharing this amazing amount of work with us. It looks very exciting, and it's very mathematically sophisticated. And I'm sure that with a little bit of practice and some tutelage, even our biologists will be able to kind of come to grips with it. It's really wonderful stuff. And thank you for sharing these references as well. And kudos to you and to your colleagues for putting this together. So with that, Jason, thank you once again. Thank you, everybody who joined us, and everyone have a wonderful weekend. And we'll talk to you next week.
Thank you so much. Thanks for having me again.
Thank you, Jason.